Hey everyone, in this AP Chem series video, we're going to take a look at the theory behind mass spectrometry. Remember from the last video that atoms of the same element come in different forms called isotopes. Like the chlorine atoms in this sample of chlorine gas, some of those chlorine atoms have a mass of 35, others have a mass of 37. Those are the two naturally occurring isotopes of chlorine. What we didn't say in that video is that you can also find out the exact percentages that each of these isotopes makes up in the sample. For example, chlorine 35 makes up 75% of those chlorine atoms, whereas chlorine 37 makes up the other 25%. In this video, we're going to find out how you might determine these percentages in real life. So a task like counting the different isotopes in a sample is one of the things that mass spectrometry is best at. Now, mass spectrometry is best done in real life, but it's not likely that your high school AP Chem class is going to allow you to do this. It's pretty expensive. So in this video, let's start off with just a broad overview of what the process might look like. The first thing you need is to get yourself a mass spectrometer. These are very large, very complex instruments. Here's some examples of what they look like. Once you've got a mass spectrometer, all you need are some atoms, like the chlorine atoms we just talked about. You inject those atoms into the instrument, it tests them, feeds the resulting data through a computer, and that computer gives you a graph that looks like this. The graph is called a mass spectrum, which you analyze to learn about your sample. So while those mass spectrometers are very complex instruments, they work on a pretty simple principle, and it's the idea that deflection can be used to indicate an object's mass. To see what I mean by that, imagine this ramp with some numbered cups at the bottom, and then imagine rolling 3 different types of balls down the ramp. We'll do one type of ball, let's say a ping pong ball with a very low mass, it's very light. Another ball with a very high mass, like this 8 ball, it's a little bit heavier, and then a golf ball that's somewhere in between. Now for the deflection part of the experiment, you can imagine, say, a hairdryer that's blowing a stream of air across the ramp in this direction. If I take that ping pong ball and roll it down the ramp, it's no surprise that because its mass is so low and it's so light, it's going to be deflected a lot. It's going to be pushed much more, or deflected much more, by that hairdryer, and it might exit in cup 5. The point is that a low mass object is going to experience lots of deflection. Do the same thing with the 8 ball, and the 8 ball is much heavier, so it might not be deflected at all, at least not in any detectable way, by the hairdryer, and it exits in cup 1. The point again, the more mass an object has, the less deflection it will experience. Of course, if we did the same thing with the golf ball, it's going to be somewhere in between, maybe exiting in cup 3. So this is the simple principle that mass spectrometry uses. A light object gets deflected a lot, a heavy object gets deflected a little, and the best part about it is once you have some deflection data, you can then analyze unknown samples. Say this tie-dye ball, I have no idea how massive that ball is, but if I rolled it down the hill and it was deflected exiting in cup 4, then I would know that its mass is somewhere in between that of a ping pong ball and a golf ball. So let's close the video by taking a look at a diagram for an actual mass spectrometer. Now it looks a lot more complicated, but this has all the same components as the balls rolling down a hill example. Instead of a ramp, we've got this long tube. Instead of balls with different masses, we're going to put isotopes of different masses through the tube. Instead of deflecting with a hairdryer, we've got a positive and negative electromagnetic field, and instead of some cups at the bottom of the ramp, we've got a detector plate at the end of the tube. So just like the first step would have been to roll the balls down the hill, the first step here is to inject my isotopes into the tube. So they get injected, and the first stage of the process is called ionization. The tube can't do what it needs to do unless an electron or two are removed from each of these atoms, making them positive. You'll see why that's an important step later on. Once the atoms have been turned into positive ions, they'll be accelerated through the tube until they get to the electromagnetic field that starts to deflect them. Because these atoms now have a positive charge, the positive pole of the electromagnetic field is going to repel or push on them much in the same way the hairdryer pushed the balls across the ramp. So here we're getting that deflection away from the positive towards the negative electromagnetic field. So as the isotopes pass through the electromagnetic field, they get separated. The heavy isotope, the Mg26, is deflected the least, whereas the lighter isotopes, the Mg24, was deflected the most, just like we saw with the low mass and high mass balls being rolled down the hill. At the end of the process, we simply need a detector that measures the mass of these particles and counts them so I can see how many of each type we had. That data goes into a computer which produces a graph called a mass spectrum. The main steps of this process are ionization, deflection, and detection, and that's the theory behind mass spectrometry. Here's a brief summary of what you saw in this video. Thanks for watching.